Section 2.1 is on page 94. It talks about matrix operations. Consider a matrix with n columns, A1, A2, all the way to A sub n. The diagonal entries of the matrix are really A sub ij, in which I equal to j. I should add that in there. Where I equal to j. So it's really A sub 1, 1, A sub 2, 2, A sub 2, 3, 3. Basically, looking at it, literally the diagonal, where those two are the same. Given an m by n matrix, whose entries are all zeros, we call that the zero matrix. So anytime you write 0 in matrix land, you mean it's a matrix with all zeros. Given an n by n matrix in which you have 1 across the diagonals and 0 everywhere else. That doesn't look pretty. Let's make it look pretty. So given 1 across the diagonal, 0 everywhere else, we call that the identity matrix, but it must be a square matrix in which the number of rows equal the number of columns. To add or subtract two matrices, they must have the same dimension. We add or subtract the matrices by adding or subtracting the corresponding entries. We're going to do an example on each. If k is a constant and you multiply a matrix by it, Ka, that's simply multiplying every entry in the matrix. Remember, matrices are a list of vectors, so the rules of vectors apply to matrices. Two matrices are equal if and only if the corresponding entries are equal. A lot of review. If you have a matrix that an m by n and another that's n by p, the inners must match and the outcome is an m by p matrix. Each column of AB is a linear combination of columns A using weights corresponding to column B, because as you see, if this is B, you end up taking A and multiplying it by each one of these vectors, which makes a linear combination. Now you gotta be careful of a few things. Do not mix real numbers with matrices. If AB doesn't equal BA, and the cancellation property doesn't hold, if AB equal AC, that doesn't mean that B equals C, and if AB equals 0, that does not mean that A equals 0 or B equals 0. Just be careful with these things. We're going to practice this a bit on page 102. They're given us few matrices, A, B, C, D, E. They say on number 2, why don't you take twice A, take A plus 2B. So A is 2, 0, negative 1, 4, negative 5, 2. This is a 2 by 3 matrix, plus twice B. B is 7, negative 5, 1, 1, negative 4, negative 3. So since those are the same dimensions, I could add and end up with the same dimension matrix. So I take 2 plus 14 is 16. 0 minus 10 is negative 10. And negative 1 plus 2 is a 1. 4 plus, again you multiply by 2. 2 is 6. Negative 5 minus 8 is negative 13. And 2 minus 6 is a negative 4. And there it is. If I take 3c, there's c right there, minus e, that's not possible. 3c minus e is not possible. And reason for that, if you're adding or subtracting, those must be the same dimension. C is a 2 by 2 and E is a 2 by 1. So not possible. And if they say justify your reason, you say dimensions don't match. And what if I wanted to find CB? There are two ways I could find CB. I could take CB, and I'm going to go by the books method. I'll show you both ways, but we're going to stick with the definition because that's how there are problems. This is 2 by 2, and B is 2 by 3, so it's doable because C is a 2 by 2 and B is a 2 by 3, and the outcome is a 2 by 3. So I could do that. I would say that that is 1, negative 2, 2, 1. And I'm going to multiply that by 7, 1, negative 5, negative 4, 1, negative 3. Now, a quick way of getting there is for you to really write a 2 by 3 and to use this shortcut, but again, we want to do it the other way. To generate this first row, backwards. To generate this first row, you're going to use the first row. For the first entry, you use the first. For the second, you use the second. And for the last, you use the last. And you multiply accordingly. So that is, you multiply those. 1 times 7, that's 7. Plus 2 times 1, that is 2. And when you get to the green, you multiply this by the green. That's 1 times negative 5 plus 2 times negative 4 and 1 times 1 plus 2 times negative 3. When you want to find the second, you would use the second. So to generate this second, you would use the second at the same deal. This times the blue, and it goes in order. Negative 2 times 4, 7, negative 14. And 1 times 1, that's why they have to match. That's why the inners must match. And then for the second, 10 minus 4, and a negative 2 minus 3. That's really the most efficient way to do this, and you could figure out what that is. That's a 9. That's a negative 13, that's a negative 5, that is a negative 12, that is a 6, and that's a negative 5. And that would be it. Now, the way they're going to do it, they're going to say, well, alright, if you're going to do this, you're going to say that is 1, 2, negative 2, 1 times 7, 1 plus. So what we're doing, we're following this. So I should say, you're going to multiply this, that's the first entry, then you're going to take 1, 2, negative 2, 1 multiplied by the second. And as you see, that's a lot of work. And 1, 2, negative 2, 1 multiplied by 1, negative 2. And it's the same idea. This right here is going to give you, this is 2 by 2, this is 2 by 1. It's going to give you a 2 by 1. It's going to give you 7 plus 1, 9. Negative 14 plus 1 is negative 13, comma, something's not right. That should have been right there, times that's 7, that's a 1. That makes this a 13. Okay. And for the second entry, you do the same thing. You say 1 times negative 5 minus 8, that's negative 13, and and 10 minus 4 is a 6. And for the third, you take the first, 1 minus 4 is negative 3, and the second, negative 4 minus 3 is negative 5, and you end up with a 9, negative 13, negative 30. Okay, I'm killing it. Here we go. Negative 13 and a 6 and a negative 3 and a 5. And I did want to mention EB. E is 2 by 1, B is 2 by 3. So if I take E, which is 2 by 1, B, which is 2 by 3, those don't match. This is not possible. And number 6, we're kind of doing the same idea again, the same analogy. If I look at number 6, and it says, compute the product, and again, that's why I want to really practice this, because they ask for that a lot. Compute the product in two ways. A, by defining AB1, B2, and then use the row. Basically what we just did, I did that already, let's do it again. So if I want to find AB, A is 3 by 2. And this is a 2 by 2, so this is doable. So one way of doing this is for you to say, well, pull this B1, pull this B2, and AB is going to equal AB1 and AB2. And if I take AB1 on the side, I'll say, let's see, AB1 is actually 4, -2, -3305 multiplied by 1, 2. That would be a 2. That would be 4 minus 4, that's a 0. That will be -3 plus 0, which is -3, and 3 plus 10, 13. Got it. So I'm going to say this is 0, -3, 13. And if I find A, B, 2, assuming that's B2, A is 4, -2, -3, 0, 3, 5, multiplied by 3, -1. That would be a 12 plus 2, which is 14, a -9 plus 0, which is a -9, and a 9 minus 5, which is a 4, and that would be the second entry right there, and there it is, the 3 by 2. They also want us to come in and say, you know what, just multiply those straight. Take 4, -2, -3305, and multiply that by 132, -1, and guess what? When I practice this enough, I'll be able to nail this one shot. I forgot I can't cut those. Here we go. And notice how this plays. To generate this first row, I'm going to use the first row. The first entry, I use the first. The second, I use the second. And that's pretty much how it works. So, in order, 4 times 1 plus -2 times 2, that's automatically a 0. So I'm going to write that down for your notes. And then for the green, I'll use those. That's a 12 plus 2. And for the second entry, I use the second, and the same idea. -3 times 1 is -3 plus 0, and -9 plus 0. For the last, I use the last, and that will be a 3 plus 10, and a 9 minus 5, and that would be simply a 0, -3, 13, 14, -9, and a 4. This is, of course, a lot more efficient, I think. And they want us to learn both because definitions always write it this way for a reason that's yet to be seen, and you'll see how that plays. Now, there isn't much really to do after this. This is pretty much what the section is about. You just have to find few of those and a few definitions to really go over. First definition, given an m by n matrix, the transpose denoted by A with a T like a power, whose columns are formed by the corresponding rows of A. Basically, the transpose switches the rows with the columns, and they have examples right here, 3 of them. I was going to work them up, but they have them as examples. If this is A, the transpose simply take the row become a column, and the row become a column. Take the row, becomes a column, the row becomes a column, and the row becomes a column. Take the row, becomes a column, and the row becomes a column. Extremely important. It's in a lot of definitions, and they give us few things to really play with. If you take the transpose of the transpose it onto each other, A plus B transpose is A transpose plus B transpose. If you multiply by a constant or scalar, the scalar is not affected. And this is very, very important. AB transpose is B transpose A transpose. It switches the order. And you should know that AB does not equal BA. We really need to get that out of the way. And there's the homework on this section, and that concludes it. Again, those are not lengthy sections. I think they're straightforward.